Okay, well, rip that guy. So we're gonna be going over a blockchain project today. We decided to go towards more projects because that'd be more interesting. But very quickly, we're gonna like spend like 5 minutes going over like a quick cryptocurrency crash course, mainly because some of the stuff is kind of necessary to understand the project like the theme we're gonna be building later. So it's gonna this is gonna be like a kind of very like simplified explanation of how all of this stuff works. If you don't understand everything, that's also fine. As long as you just understand the main like gists of everything that's happening. So cryptocurrency, I'm sure you guys know, it's a form of digital currency. It's like currently like the new wave stuff like Bitcoin, Ethereum, Dogecoin, whatever. Um, However, today, what if we ever talk about like a specific coin, we're gonna be referencing Bitcoin because it's like the parent of all the cryptocurrency, and that's what our blockchain is gonna be mainly based off. And so we're gonna go over these main ideas and concepts before we get into building the blockchain. So first, digital signatures. Basically, if you're like sending money online, we need some way to verify that there has been online transactions, right? In real life, you normally, you sign a receipt or something, whatever, very similar, right? Verifying the transaction. However, you need to do this digitally. So if you try to like sign something digitally, it basically boils down to zeros and ones, right? Because at the end of the day, no matter what your signature is, it's going to become zeros and ones because that's how everything is digitally. And that's very easy to like copy and paste over and over again if someone managed to get that string of zeros and ones. So that's why we need to like prevent forgery while still using digital signatures. So to do that, we're going to be using a secret slash private key, right? So that's one key, and then a public key. And these are like a key pair. They're like paired together, basically. Obviously, the private key is only accessed by you. The public key can be viewed by anyone. And that's like how the main thing works. So the signature that we're going to be making is encrypt with your private key, and it's based on the message slash transaction. And the message might be something like Alice sends Bob $10, right? And then you would encrypt this message with Alice's private key because Alice is the sender, and that would give you the signature from Alice for this message. And the use of this is that therefore the signature will vary and the signature will change each time the message changes. So if I know this message becomes like 101 when encrypted, I can't just copy and paste that anymore because the next message, which might be like Alice sends Joe $10, is not going to be 101 anymore. The signature is going to change because the message has changed. And we can still verify that it's valid using the signature, the message, and Alice's public key. And with all of these three together, we put in a function and it returns true or false if it's valid or not valid. And then to do all of this, you commonly use SHA-256. It's a one-way cryptographic hash. We're not going to get talk about how it works. Just know what it is. It's commonly used. An example hash looks something like that. It's pretty long. It's pretty random. And so that's all for digital signatures. And then now we're going to talk about the ledger. So a ledger is a digital global record of all transactions. So it's like a bank record and it like kind of keeps track of every single Bitcoin transaction across the whole globe. And it's important that it uses unique IDs. And this is to prevent fraud because if you knew that the message Alice sends Bob $10 encrypted with Alice's private key gives you the signature ABCDEFGHI 1 2 3 4 5. You could hypothetically forge the same transaction many times, right? I can use the same signature and put it again on the ledger and say, hey, Alice sent Bob another $10, even though Alice didn't approve that. So to make sure this doesn't happen, we use different IDs to make each message different. So this one, like the ID could just be simple as like 1 2 3 4 5, or it could be like really random. But basically now, these messages, which do the same thing, right? Send Bob $10 from Alice. They have a unique ID here, so the encrypted signature is going to be different. And then also the ledger automatically checks if you are overspending. So I can't send someone $1,000 if I don't already have $1,000. So to do that, it takes in previous transaction inputs and it also takes transaction outputs. And it's important that transaction inputs are basically references to previous transaction outputs. And that's how it continuously checks over and over again how much money you do have. You never actually like have any money in your wallet. Instead, what you have is like a list of transaction inputs and outputs that show, hey, I had $10, I gave away $5, I got 10 more dollars, right? And that's basically your wallet. This part's not that important though. And then decentralized. So this is just a concept. It's pretty confusing, decentralized versus centralized, but basically decentralized allows us to make and verify transactions without a central authority. So like there is no government like doing all of this stuff. There is no like group that's in charge of it. Instead, the public is doing all of this. And that's the important thing about Bitcoin, which is why it's so like special. And to do this, everybody has a copy of their own ledger, and transactions are broadcasted, and miners right add transactions onto their ledger using proof of work. We'll talk about proof of work later, but basically, everyone has a copy of their own ledger, and then miners add the transactions onto the ledger with the proof of work. And you trust the ledger with the most computational work, which is your proof of work. So if someone wants to forge a transaction, they would basically need to break the proof of work system, which would require a lot of power and like a lot of power over like the public. You would need to control like 50% of all miners basically. But that's also not too important. So now proof of work. This is also commonly known as mining. So when someone says like, I'm mining for Bitcoin, this is what they mean. So a proof of work, all it is a SHA-256 hash with a lot of zeros at the start. So an example proof of work would be something like this, where there's a bunch of zeros at the start, and the more zeros, the harder, because you have to generate this hash, and it's not easy to get a bunch of zeros in the front. So the more zeros there are, the harder it is, and the number of zeros is continually increased over time. So on average, it takes 10 minutes per proof of work. So it takes about 10 minutes for all the miners in the world to for one of them to manage to get the proof of work for Bitcoin. For other coins like Dogecoin, it's not 10 minutes, it's like 25 seconds or something. But it varies from coin to coin. And so the SHA-256 proof of work takes a lot of time to compute because there is no like formula. It's simply a guess and check. And so miners try to be the first one to get the proof of work. So it's literally like a lottery. And those who win the lottery, they receive a certain amount of Bitcoin. That's like your mining reward, I believe is what it's called. And it goes in half every 4 years. So if the miner, like, each miner who wins that lottery gets like 25 Bitcoin this year, in 4 years it'll be 12.5, and it'll keep on having. So there's only like a certain amount of Bitcoin ever in circulation. And so the proof of work is lastly is based off the list of transactions. So if the ledger or transactions are modified, the proof of work also has to be recalculated, which is pretty important. So therefore the proof of work is extremely secure. And lastly, we're going to go over blockchain. There is no like slide for this because we're going to be building it. But basically, all you need to know is a blockchain are a bunch of blocks, and a block is basically a transaction or like a list of transactions slash a ledger. And each block contains its own hash and the hash of the previous block, and they're combined to form your blockchain. And so that's all for the cryptocurrency crash course. Hopefully that made some sense. I think now we're just gonna start coding it. So I have my Eclipse open. Hopefully you guys can see this. These are just some master files. Um, you guys can follow along if you want. Don't expect anyone to, because it's kind of fast paced. We don't have a lot of time. But basically, this is in Java, right? So you can use any editor you want, VS Code, whatever. But it's important to use something where you can import libraries, because we're going to be importing a JSON library. Um, JSON is kind of interesting. It's basically JSON, which is right. I'm not going to explain what JSON is. If you know, you know. If you don't know, all need to know is basically um, like some sort of method for like displaying objects. That's the best way I can describe it. Basically, JSON is JSON, except it works for Java. So to import it, you will need to download the .jar file and add it to your user libraries. I have already done that, so now all I need to do is go into my build path and configure it for this specific project and add a library. Yes, I'm going to be adding JSON lib. So now we can use JSON inside this project. And then so now just to start off, we're going to create our main file. Like this is a main file with the main function and stuff. And we'll just call it blockchain.java. All right, that's cool. And then I'm gonna create some other files too, and we'll fill this one in a bit later. So we're gonna call one block.java, and this one is your block class, right? It contains your block. So for the block class, we need to import java.util.date because is it not util? It is util. Java.util.date because we're gonna be using timestamps for each block. So each block is also gonna have a timestamp. And then each block is going to store a string, which is their hash, a string, which is the previous hash, and then they're also going to store a private string this time, which is the message, aka like the transaction, right? This is a transaction message, or data. It might be referred to as data too. It's the same thing. And then we're also going to have a private lon that is storing the timestamp. And it just stores the time it is created. So because this is a class, we're also going to need like a regular constructor. It's going to take in the string's data and the string's previous hash. And then we can just set this.data equal to data and this.previous hash equal to previous hash. And then this.timestamp can be set into new date.get time as a long. Oh, what happened here? Oh shoot, this is supposed to be message. Alright, so that's just like the very small functionality, very simple. We'll update this and make this more fancier a bit later. But that's basically the main structure of our block. It stores a hash, previous hash, message, and timestamp. And then so now we're going to be needing to do the encryption part, like the all of the SHA-256 stuff. So we're creating another class. It's called string util. Basically, it's just a utility class with a bunch of helper functions to do stuff like this. So I'm just going to copy paste some code because I'm not going to explain any of this. All you need to do is it applies SHA-256 to a string and it returns the result. So that's all it does right here. And then basically, we're also going to need a helper function inside our block class to calculate the hash. So we're going to be using this apply SHA-256 inside here. Basically, it's called string calculate hash, and then instead of data, right, this is message. So how this works is it takes a calculated hash and it uses the string util class and it uses that function that we just made, and it takes in the previous hash, the timestamp, and the message, and it returns this calculated hash. So this gives us a hash which hashes the previous hash, the timestamp, and the message. And then we need to add the new hash into the constructor. So this might be a bit confusing. Hopefully you guys can follow along. But we can just like test it here basically by just putting in a main method into this class, right? This is like our main class, tester class. And so what I have here is we have a block. It's called Genesis block because it's the first one. And then it says, hi, I'm the first block. And then it has a 0 here. The 0 stands for the previous hash because there is no previous hash because it's the very first block. And it just prints the hash for block 1. Then this is the second hash. For the previous hash, it takes the Genesis block's hash, right? Because that's the previous hash. And it does the same thing. The third block does the same thing, except it takes the second block's hash. So hopefully if we run this, it gives us 3 different hashes, and for hashes for block 1, block 2, and block 3. So it's working so far. And then we need to make this like a blockchain, right? So to make this a blockchain, we're going to import the ArrayList class. Hopefully you guys know what that is. Basically, it's like an array, but it is dynamic, so it's like more of a chain, or we can kind of use it as a chain. And I'm also going to be importing the JSON we had earlier. And then this is just some simple code. basically in here we're going to create our blockchain. The element is going to be type of block, and it's going to be called blockchain, and we're just going to declare it like a regular array list. So basically now we're using some more of the ArrayList functions. The first block is simple, it's Genesis block, it uses 0. The second block, however, in the previous hash function, it takes in the previous block's hash, right? This is what blockchain.get, blockchain.size minus 1.hash is doing. And so we just need to copy and paste that for each of them. So it's more like redundant and able to be replicated. And this is a blockchain JSON here. I'm not going to explain it because I don't know how it works either, but it's the library that we imported. And so now we can run this code again, and it's going to look much better now. Okay, so basically this is the first block. This is a hash. Previous hash is 0. That's the message. The second block, this is the new hash. The previous hash is the same as this hash, right? Notice that. And the third block is previous hash is the same as the second block's hash. And that's how we can validate our blockchain. We can check each previous hash. So now we're going to create a static method in here that can help like test if our chain is valid. So it's going to be called boolean is chain valid, and it just returns a true or false. And then we're going to take current block and previous block, and we're going to store each block a bit later. So we're going to run a for loop this time, right, to loop through every single one. We're starting at 1 because we don't need to check the first block because there is nothing behind the first block, if that makes sense. And then so now we'll initialize these. And then current block, this one's going to be previous block. And then so now we just need to put in a couple if statements. So I'm going to copy and paste these in. Basically, this one just checks if the current block's hash is equal to current block.calculate hash. If basically checks if they're not equal, and if they're not equal, it returns false and it gives you an error message. This one, it does the same thing except it compares the previous block's hash with the current block's previous hash, right? Which we showed earlier, which is like this one and this one, comparing those two. And same thing, it returns false if it doesn't work. And then if the for loop runs properly, we're just going to return true because the chain is valid. And so that's all for the isChainValid method for now. And so now we want to like start mining some more blocks. Basically, to mine blocks, we're going to take in a difficulty factor. The difficulty factor is basically how many zeros in front of your proof of work. So this is the function that we're going to be using. We're going to need increment ID plus plus, and ID will just have it up here. So ID was the thing we were talking about earlier, which was the unique ID to make sure you can't just like copy and paste the same transaction. And then so mine block, it takes in difficulty. Difficulty is the number of zeros in front of your proof of work. And then it creates a string with that with however many difficulties. So like if difficulty was 5, it would create a string of just 5 zeros. And then it checks if the hash's substring, the first 5 characters are equal to the 5 zeros here. And if it isn't equal, it's going to increment the ID and recalculate the hash. And if it is equal, it will stop and it'll say the block is mine, and it's going to send out the hash. And so this is more of like an actual blockchain now, except we're also going to add the ID inside our calculated hash. Oh, why is this not working? It should be a toString. Okay, so now to actually use the difficulty, we need to create a static variable up here in our tester class, right? To actually like be able to use it. So we're just gonna call it a difficulty. I'm gonna set it to 5 for now, and I'll demonstrate like 6 and 7 and show you guys like how long it truly takes. But basically now we're gonna copy and paste some more code here. So all of this stuff, basically, the new stuff is just trying to mine the block. That's really all there is new to it. It's still 3 blocks. We're just trying to mine it now. And then also in our testing, we want to testing that if the chain is valid, we want to make sure that each block has the proof of work mined, right? So we want to make sure each of the blocks has the proof of work mined. So like the 0 to difficulty equals a hash target. The hash target, which we haven't initialized yet, is the same thing as earlier. It's just a string of however many zeros, difficulty amount of zeros. And so I think we can test this code now. So if I run it, it should. So it's trying to mine block one, and it's mined. And then we notice that the proof of work, right? It has 1, 2, 3, 4, 5 zeros here. This one also has five. This one also has five. And it was pretty quick. Like I think it took like maybe less than 10 seconds. But now if we up the difficulty to six, so if we're asking for 6 zeros now, it should take considerably longer. Yeah, so oh, it was actually pretty fast. Okay, let's test it again. Let's try seven. Yeah, so this is gonna take a while. So I guess we can run this in the background. Um, but basically, we're all done with the blockchain now. I'm gonna demonstrate some more of it, like I'm using wallets and stuff. But I don't know how long this is gonna take. Normally six takes a while. I'm using like a regular laptop, so it's like not too high end, not too like it's not like a supercomputer used for mining. If I was like using a PC or something, it'd be much faster. Um, but like for reference, I believe like Ethereum's proof of work is around like 400,000 zeros or something. It could be wrong. Actually, I think that is wrong because I don't think 400,000 is. I think that's too big. But um, basically, that's what people say when they're mining for different blocks. They're just basically trying to get that many of zeros in front of their proof of work. And so that's why like whenever you hear about like Bitcoin miners and like how they're like using up all of the energy in the world, like melting the Arctic, it's kind of true because they're using a lot of computing power, to try and guess and check all of this stuff. I'm just gonna stop running this because it doesn't seem to be working anytime soon. But basically, um, if we let it run for a while, a bit longer, it would just keep on while looping and testing and guess and checking until it reached 7 zeros. So yeah, I think I'll just bump it down to 5 for now. And then we still have 12 minutes, which is actually pretty good. So I'm gonna show you guys blockchain part two. This is like much more of an actual blockchain. This was just like a demo. Oh, didn't mean to do that. Okay. Um, so we can open up these files. But basically, it's also importing another JSON, which is called Bouncy Castle. I'm not 100% sure what Bouncy Castle does, to be honest. But it's used inside this one. So this is like this is all entirely based off of the demo, the lesson thing I just showed earlier. Except it has much more classes, much more stuff. And then I'll show what it actually is. There's a lot more new stuff, but we'll just start from the top. I think I'm gonna start with wallets. So wallet is another class. It stores a couple important things. So it stores a private key, your public key, and it stores a hash map of um, UTXOs. UTXOs basically don't worry about it. Basically, just know this hash map stores your transaction outputs and inputs. So essentially, this is how much money you have, right? Because I told you earlier, we don't actually like ever store a balance. Instead, we just store a list of transactions, which we can use to calculate our balance. And the private key and public key, it's used. There's a java.security.ecgen parameter spec thing. Basically, what it is it's a built-in Java function that allows us to generate a key pair using elliptic curve cryptography. I'm not too sure about anything else other than that. All I know is it generates a key pair, so like these are pairs basically. And this is where it generates a key pair. It uses all of that stuff. We're not going to get into it. Just know that this generates our key pair. And then this gets your balance, right? So it just loops through that hash map we had earlier, and then it just totals up your balance basically, and it returns it. And then so this is the transaction function with send transactions, right? So it takes in two parameters, your recipient and the float value, right? So who you're sending the money to and how much you're sending. And then it does some other checking, right, to make sure you have enough funds, right? So if you don't have enough funds, it'll send you this error message. And if you do have enough funds, it will start sending it over using the transaction class. What the transaction class? So this is a transaction class. It stores a bunch of other stuff, the transaction ID, the public key sender, and the public key for the recipient. No, it doesn't store any private keys, right? Because that's all private. It only takes the public keys, which anyone can get. And it takes the transaction inputs and outputs, and this is where it creates the signature. And float value is the amount of money we want to send. We don't need to worry about sequence, it's not that important. This year constructor is pretty self-explanatory. Process transaction does some like basic checks. It checks that the signature is verified, otherwise it gives you your error message. Otherwise, it gathers the transaction inputs to make sure that they're unspent and you have enough money. And then it does some more checking, and it checks if the transaction outputs, how much you have left over to keep in your account. And then it adds it back to your list, and it removes the inputs from your list. So it basically updates how much money is in your wallet and their wallet. And then get input value, it just gets input value, generates signature, generates your signature, verifies your signature, get output value, does the opposite of get input value, and calculate hash, it calculates the hash of your transaction. So all of this stuff is helper functions, pretty simple. This is the main checking function. And then it uses transaction inputs and outputs, which are also classes. Transaction input class is pretty easy. It just contains an ID and the UTXO list. Remember, I said outputs are basically references to your inputs or previous inputs. Um, so that's why transaction output is a bit longer because it contains the output of the recipient, the value, and the ID. So like I know that hey, Alice sent me $5, or hey, Bob sent me $5 or something. And so that's the transaction output class. So we've went over all four of these classes already. String util is the same thing except it has some more helper functions. This one applies the ECDSA, which was the elliptic curve cryptography signature. This one verifies the same thing above here. And then this is just more just more helper function. The get Merkle root is used within the UTXOs. We're not going to get into it. This is our main testing class. I'll show it in a second. We first need to go over to block.java. So block.java, it has basically all of the same stuff, except there's one more function, right, which was add transaction. Basically, it just adds a transaction. That's all it is. It does use the transaction class, so most of the stuff we already went over in there. So yeah, this is pretty confusing. It's a lot of stuff, and because we didn't like code it from ground up, it's like a lot at once. But basically, in here for demonstration purposes, right, we have two wallets, wallet A and wallet B. They're going to be sending to each other, right? That one's Alice, that one's Bob. And then the difficulty is still going to be 5 for demo purposes, and minimum transaction is 0.1. We want to make sure you're sending over zero point 0.1. And then you create your very first transaction, which is the Genesis transaction, because right, you have to start with money somehow. Like normally when you're using Bitcoin, you start with money by paying real cash to someone else who gives you Bitcoin in return. But the very first transaction, they didn't have that like ability to do that, so they automatically got some cash basically because it was the very first one. This is a bouncy castle. I don't know what it does. It's apparently a security provider, basically adds our blocks to the blockchain. And then so we're going to create our wallets, and that's going to be our static wallet. This is the Genesis transaction, which it sends 100 coins to wallet number A. So we can close this to get some more space. So it takes Genesis transaction, creates a new transaction. It has all of the stuff, the public key, the wallet's public key, how much money? 100 coins. And no, right, because it's the very first transaction. The generate signature uses a private key, gives you the ID of 0 because it's the first one. And then for outputs, it adds in the previous inputs, not important, and it adds more stuff into your list. And then it's creating and mining the block. And then for blocks 1, 2 to 3, it's all the same thing, except block 1 is attempting to send 40 bucks to block, sorry, block 1 has wallet A attempting to send 40 coins to wallet B. Block B has wallet A to attempt to send more funds than it has 1,000 to wallet B. So this one should get blocked or invalidated. And block 3 has wallet B sending back 20 funds to wallet A. And then it checks if the chain is valid at the very end. So we can run all of this code. Oh yeah, is chain valid? It has a lot more stuff this time, mainly to this time verify the transactions as well as the just regular blocks itself. So we can ignore this stuff. This is because I'm using the .jar JSON and it's not been updated, so it's has some warnings. Um, it should be fine though, I hope. So it's mining the Genesis block. The transaction has been added. The block has been mined. There's 5 zeros. That's our proof of work. The difficulty is 5. And it says wallet A's balance is $100. And then wallet A this is block number 2, right? It attempts to send funds 40 to wallet B. Successfully has been added, 5 zeros here. Wallet A's balance is now 60 and wallet B's balance is now 40. Now it's attempting to send $1,000, which it doesn't have. So the transaction is therefore discarded. The block is still mined. The balances are still outputted, but the balance has no like difference and no money was exchanged. The last one, wallet B is attempting to send funds 20 to wallet A, is successful, added to the block. Now wallet A has 20 more, 80, wallet B has 20 less, 20. And then it checks the blockchain is valid and it says blockchain is valid, right? It runs through all that stuff. And so that's basically all for the demonstration. Hopefully that made some sense or you understood a bit more about blockchain and cryptocurrency in general. If you guys have questions, you guys can let me know right now. Otherwise, we'll close the meet in a couple minutes. Huh. Uh, yeah, so to answer that question, uh this isn't like a very like well-made blockchain, right? This is in no way like, you would never like actually implement this like in practice or, in actual practice. This would not be implemented. This is more like a demonstration. It has like a lot of flaws here and there if we're actually going to try to use this as a blockchain. Um, However, it's for demonstration purposes to kind of show how everything works. A real blockchain wouldn't have so many of like all of these. It wouldn't be like as manual as it is right now with all of this stuff here. And instead, it would just ask for some inputs and stuff, and it probably wouldn't just manually create Sue wallets and such. But it's pretty similar in everything else. Other than that, it's also coded in Java, which I'm pretty sure like shouldn't be coded in Java, but I guess it works. All right, I'm going to end the Zoom now because I assume you guys don't have any questions.